All right, we're going to do one more construction here, and this one is probably the most complicated. This is drawing a parallel line through a point, not on the line. So my example here, you have point A, and then you have this line beneath it, and you'll notice that A is not on the line. So what I want to do is to construct a line through A that is parallel to this line. Now, you might say, well, wait a minute, that's kind of horizontal. Let me kind of do a horizontal here, and then I'm done. You might be close, but again, we're trying to be perfect, not close. So here's how we do this one. We actually are going to start by drawing a second line that goes through A and that intersects the first line. Okay, so I'm drawing this line here. Let's call this line L, and the new one is line M. So line M, you'll notice that it certainly crosses line L, so it's not parallel to it. And it does go through A, which is what I want. We just created an angle. So if I call this intersection point, I'll make that B. Well, what I want to do is to take angle B, and if I can copy that here with A, then I should have a parallel line. So we're going to take the last construction we did, the congruent angle, and we're going to basically do the same thing. So we're going to anchor on B. We're going to start on B, and I'm going to draw an arc that goes through both sides of the angle, and it creates 2 points. I'll call these points C and D. Now I'm going to come up here to A, and I need to draw the same arc. One of the other things, if you find that your arcs, that this is moving while you're doing it so that your arcs aren't as good, if you press less hard, if you press a little bit softer, it's not going to slide as much. Okay? Now, this arc only created one intersection point. It's the point that corresponds to C. I'll call that C prime. If I can figure out where D prime goes, then we're done. Well, let's measure the distance from C to D. So to do that, I'm going to anchor on C and adjust the setting here so that the hole goes right on top of D. Let me verify that. All right, that looks okay. And then from C prime, let me draw the same arc. Now, if I've done this right, there's D prime. If I connect A to D prime, so let me try to be accurate here. Does line AD prime look parallel to line BD? I think it is, actually. That looks pretty good. I'm going to put those little parallel marks on there. So I can say line AD prime is parallel to line BD. Okay, so I just constructed a parallel line by doing that. Now you can practice it over here. I'm going to show you one more proof though, and it has to deal with parallel lines. I'm going to put it on the back of this. One of the rules that we've learned is that when you have two parallel lines cut by a transversal, the alternate interior angles are always congruent if these lines are parallel. So parallel implies alternate interior angles are congruent. Okay, so now what happens, the converse, does that work? If the alternate interior angles are congruent, does that mean that the lines are parallel? That's the question. Okay, so we know if the lines are parallel, we know that these are going to be congruent. Does the converse also work? If alternate interior angles are congruent, does that make the lines parallel? So if you knew, so let's say you have a picture here. What we're asking, if we know that, then can we say that the lines are parallel? That's what we're trying to show. That's what we're going to try to prove. So I'm going to do this with a different kind of proof. I'm going to call this an indirect proof. Okay, and this gets into some higher level mathematics here. But the idea of an indirect proof is we actually start by assuming that the conclusion is false. Now the conclusion is that the lines are parallel to each other. Okay, so we are going to assume that the lines are not parallel. So I'm actually going to draw this a little bit differently here. I'm going to draw the lines where they're obviously not parallel, which means that if they're not parallel, they have to intersect at some point. Here's the transversal. Now remember, we are being given that the alternate interior angles are congruent. So we do have this right here. So in this case, I'm going to call these angles 1 and 2. So we're assuming that the lines are not parallel. Okay, so if we call the lines A and B, I probably should have done that up here. So, and here's A and B again, but obviously you see that A and B are intersecting each other, that they're not parallel to each other. Now there's another angle here. We know, I'm going to label this one here as angle 3. We've got a triangle here. And there's a rule with triangles that an exterior angle is equal to the sum of the two remote interiors. Angle 1 is equal to angle 2 plus angle 3. That is called the that's called the exterior angle theorem. That this angle is equivalent to the sum of these two. Now, what this leads us to is a situation that we know that these are positive numbers. Okay? As an example, let's say that this was 50 and this was 60. Okay, here's angle 1. Well, 50 and 60 means that these are equal to 110 for that. Since these are positives, when we add them up, this sum has to be bigger than each of these numbers, right? If 50 plus 60 is 110, we know that 110 is bigger than 50. We know that 110 is bigger than 60. So in other words, we don't know the numbers coming back to this picture, but if angle 2 plus angle 3 is equal to angle 1, then that means that angle 1 has to be bigger than angle 2, and angle 1 has to be greater than angle 3. But we have a problem here. We have reached, I'm putting an X here, we've reached a contradiction. Because remember, what was given to us? What was the information? The information was that if we were given that the alternate interior angles were congruent, right? In the converse, if the alternate interior angles are congruent, then we're trying to show that the lines are parallel. Well, wait a minute. In this case, angle 1 is greater than angle 2. So this is contradicting what they told us is true. So if angle 1 and angle 2 have to be the same, but we're showing that they're not the same, then we have a problem here. And the problem is, remember, we started by assuming that our conclusion was false. We were assuming the lines were not parallel. And then we followed from that, and by assuming that, we reached something that cannot happen. So we reached a contradiction, which means that the assumption was false, which means that the original conclusion must be true. So what we've done, and I know this is a little bit tricky here, if the lines are parallel, then the alternate interior angles are congruent. The converse, if the alternate interior angles are congruent, if you know this, then you know for a fact that the lines have to be parallel. And this is the cool thing about proof, is that we have all these rules in geometry, but if you ever doubt them, we can prove them. Okay, I'll show you one more. I'm sorry, I keep coming back to things here. I'm going to go back to the angle bisector. Well, just like the perpendicular bisector, with the angle bisector, there's a rule that says all points on an angle bisector are equidistant from the sides of the angle. Okay, now what that means is that if I pick a point on the angle bisector, let's say I pick a point here and I call this E. The distance from E to this line, and distance in this case is a perpendicular, is going to be the same as the distance from E to this line. If a point is on an angle bisector, then that point has to be equidistant from the sides of the angle. If I picked a second point, if I pick one, let's say I pick D actually. If I draw, so I'm trying to draw a perpendicular here, and here I'm approximating. These have to be equidistant. Okay, and just to show you why that would be true, again, I can use congruent triangles. If you look at these two triangles here, let me draw them out. Okay, something like that. We bisected the angle, so we know that those are congruent. We know that these are congruent because they were drawn using the same arc. And we also have a common side here. So let me label the points here, A, B, E, and that's C. Now, if I'm writing out this proof, we would say segment AB is congruent to segment AC because they're drawn from the same arc. We know that angle BAE is congruent to angle CAE here, because that's what we just did with the angle bisector. We bisected. AE is an angle bisector of angle BAC. We know that segment AE is congruent to itself by the reflexive property. Now, based on this information here, the triangles have to be congruent. Triangle BAE, that's the top triangle, is congruent to triangle CAE, and that's called side angle side. The side angle side postulate. Therefore, and this is the last thing here, therefore, the distance from E to B, segment EB, has to be congruent to segment EC, and the reason is CPCTC. I didn't write it down before, but what that stands for is corresponding parts of congruent triangles are congruent. C, P, C, T, C. If these triangles are the same, then their corresponding pieces have to be the same. So these angles would be the same. And what we just proved was that, hey, point E is actually the same distance from B and C. Okay, so there's some complicated stuff going on here, but this is the cool thing with geometry. We kind of proved it, we can construct it, but we can also write it out and actually justify what we've done. So if you're looking for more practice, you can certainly do more congruent angles. You can do more angle bisectors. On the last page here, there's a couple extra examples if you want to try those. And that is the end of the notes.